Hello everyone. In this video we will discuss L'Hospitals Rule. In this video we will revisit the concept of limits that we were presented in Calculus 1. Remember that limits were used to introduce the concept of derivatives. This time, strangely enough, we will make use of derivatives in order to evaluate limits. Here is the statement of L'Hospitals Rule. Let f and g represent functions that are differentiable on an open interval containing x equals a, although differentiability is not necessarily needed at x equals a itself. And suppose also that the limit as x approaches a for both f of x and g of x are 0. Then, according to L'Hospitals Rule, we can replace the limit as x approaches a of f of x over g of x by the limit still as x approaches a, but for f prime of x over g prime of x. In other words, f and g are replaced by their respective derivatives. This is not the quotient rule. First example, observe how in this limit as x approaches 1, both x squared minus 1 and 3x minus 3 go to 0. So this is an indeterminate limit of the 0 over 0 form. X squared minus 1 and 3x minus 3 are both polynomials and are therefore differentiable. So according to L'Hospitals Rule, we could replace them individually by their derivatives and reevaluate the limit using those simplified derivatives. Differentiating x squared minus 1 gives 2x, and differentiating 3x minus 3 gives 3. And we're ready to reevaluate the limit with this simplified expression to get 2 over 3. You've noticed that I've incorporated a little HR symbol at the step where L'Hospitals Rule was applied. In the second example, we have a limit as x approaches 0, where e to the 2x minus 1 and 2 to the x minus 1 both head towards 0. This is once again an indeterminate form of the 0 over 0 type. Exponential functions, as those you see, are differentiable, and therefore, according to L'Hospitals Rule, we can replace the individual numerator and denominator by their respective derivatives. So differentiating e to the 2x is e to the 2x times 2 because of the chain rule applied to 2x, and the derivative of 2 to the x is 2 to the x ln of 2, which is a basic exponential form a to the x. In both cases, the derivative of 1 became 0. We're now set to reevaluate this new limit with x going to 0, and a determinate form 2 over ln of 2 is obtained. In our third example, we have, once again, two polynomials, top and bottom. Were you back in Cal 1, you could potentially use factoring in order to solve this form, which is also of the 0 over 0 type. However, L'Hospitals Rule would also allow you to replace the original limit, as x approaches 2, by a new limit that involves the derivatives of the individual numerator and denominator. This prevents you from having to use factoring. The derivative of the numerator is 2x minus 4. The derivative of the third degree polynomial at the denominator is 3x squared minus 4x minus 4. Curiously this time, you'll notice that trying to do direct substitution would give you a new 0 over 0 form. Well, that's fine, and L'Hospitals Rule can be applied a second time when necessary. Differentiating the top and bottom, we will get 2 from the numerator's derivative and 6x minus 4 from the denominators. Once again, trying this new limit by direct substitution, you will get 2 over 8, which is a quarter, so a determinate answer is observed. Where L'Hospitals Rule becomes very handy is when techniques learned in Cal 1, factoring and canceling, rationalization, just to name a few, cannot be used at all. In this example, sine of x and the cube root of x both head towards 0 as x approaches 0. This is a 0 over 0 form, for which all strategies you've learned in the past would have failed. L'Hopital's rule, however, allows you to replace numerator and denominator by their respective derivatives. The derivative of sine of x is cos of x. The derivative of the cube root of x, which we can think of as x to the 1/3, is 1/3 x to the minus 2/3 by using the power rule. Now, before going any further, remember that fractional and, in this case, negative exponents can or should always be transformed. So before proceeding to the next step, I have rewritten this expression with the exponent written as a positive exponent brought to the top, and dividing by 1/3 is equivalent to multiplying by 3. So this is not L'Hopital's rule, but rather just an algebraic step. As x approaches 0, this new limit tends towards 0 by direct substitution. So occasionally you will have a combination of L'Hopital's rule or algebraic manipulations to be done on a limit. Here's an important note: L'Hopital's rule can just as well be applied to infinity over infinity limit forms, which are also indeterminate. Here's an example that is of infinite over infinite form by direct substitution, and it involves a polynomial, x squared plus 5x plus 4, as well as a combination of polynomials and logarithms at the numerator. These are both differentiable functions on their domain. L'Hopital's rule can be applied because of an infinity over infinity form being observed. So differentiating the numerator through a product rule and the denominator using the power rules. So at the top, ln of x plus 1 through the product rule is obtained. 2x plus 5 is the derivative of the denominator. And we would be ready to try L'Hopital's rule again, or at least to verify if we can use L'Hopital's rule. Direct substitution at this stage will give an infinity over infinity once more. So L'Hopital's rule allows us to replace, once again, this limit by the limits of the individual derivatives of top and bottom. The derivative of ln of x is 1 over x, and the derivative of 2x plus 5 is 2. And this time, by direct substitution, we get a determinate answer of 0. Few warnings before we move on to our next chapters. L'Hopital's rule will backfire if you do not use it appropriately. For instance, here is a limit that is simple enough as x goes towards 1 and is applied to the ratio 7x plus 2 over 5x plus 4. These are differentiable functions, and if you were to replace top and bottom by their derivatives, you would get an outcome that is 7 over 5, and the limit on this constant would still be 7 over 5. However, keep in mind this limit is actually wrong, because if we had done direct substitution from the start, we would have had 1. Keep in mind L'Hopital's rule can only be applied if a 0 over 0 or an infinity over infinity form is obtained from the onset, which was not the case here. Warning number 2, L'Hopital's rule is not always the best method to use. So although we are tempted to use it all the time, it may actually not always be as useful as we would think. For instance, here is an example where we have an infinity over infinity form because both top and bottom have behaviors that are dictated by the biggest power term, so the x to the 5s. It would require 5 derivatives before these powers would reduce to something that is more manageable, or that would not reveal an infinity over infinity form anymore. In Cal 1, you were probably taught to factor out the biggest power The reason for this is that common powers x to the 5 can then be cancelled, and all of the terms that are divided by powers of x, in this case, would actually go to 0, and we would get 1. So strategies from Cal 1 here would be much quicker than to apply L'Hopital's rule 5 times. A second type of situation where L'Hopital's rule may not be the best method to use is when it involves root functions. So here's an example where x going to infinity for x over root of x squared plus 1 does reveal an infinity over infinity form, and these are differentiable functions. However, if we do apply L'Hopital's rule, and I'll spare you the details of the derivative, but essentially we treated x squared plus 1 to the 1/2 as a power rule at the bottom. And what would happen if we simplify this expression is all we would get is the reverse of what we started off with, which is still infinity over infinity. And applying L'Hopital's rule again would probably just bring you back to the starting point. So in other words, there is no simplification that comes from applying L'Hopital's rule. We go in circles. In Cal 1, you were most likely taught that for expressions that involve powers, whether they're in roots or not, can be dealt with by extracting the biggest powers and simplifying whatever common powers there are before trying direct substitution again. So those are still valid techniques.